I'm elated to welcome Mr. Manan as our guest speaker. He is the CEO of Silicofeller and president of One Quantum Bangalore. He is an IBM certified Qiskit developer and a strong advocate of quantum computing in India. He has over 15 plus years of experience in the computer industry and is passionate about the quantum computing. He is involved in development of quantum computing chips and superconducting quantum circuits. He is now working to make the India as a leading hub for quantum research and development. Quite an inspirational journey, sir, and we wish you all success in making your vision come true.
Thank you so much for the opportunity. And uh, like I said, I'll be start presenting now, and I'm glad that I'm here. So first of all, I just wanted to talk about what we are doing as a company. So we are trying to build quantum computing chips and applications. So that is where our journey began. So now coming back to the talk, fault tolerant quantum computing. So most of you must be aware that right now we are in the stage of noisy intermediate scale quantum computers, and very soon we will be entering the age of fault tolerant quantum computers. So what makes a quantum computer fault tolerant? What are the ways a quantum computer can be built? I'll be talking about all those things in the slides to come. So like I said, where are we right now? We are in the age of noisy intermediate scale quantum computers, which means that they are prone to errors right now. So they are in the very nascent stage, and to do something very useful, we need thousands of qubits to do something useful. We are seeing applications, but they are not as advanced as we need them to be. So today, if we'll take like hundreds of qubits, those are called the noisy intermediate scale quantum computers. And most of you might be familiar with bits and qubits by now, so I don't think I need to discuss more on that. But one more important point that I needed to mention out, that if a quantum computer is built using 275 qubits, it could represent more computational states than there are atoms in the known universe. So that is the power of just 275 qubits, that 2 raised to the power 275. So that's like a big number in itself. So that is where, with every single additional qubit, the computational size gets doubled, because then it becomes 2 raised to the power 276, that is a double of 2 raised to the power 75. So it took 60 years for classical computers to reach a point where they are right now. All the development that has happened in the past 60 years, quantum computers will need to go through the same process in the next 2 to 3 years. And that's a quote by Jake Gambetta, which is the IBM president. And he has said that that is the state of development that is happening. It is the most powerful technology in the history of mankind, and it is progressing at a rate that is so fast that people aren't even getting to know that it is existing, and it is evolving at such a high rate. So apart from this, these are that how do we have a quantum data center? So that is going to take a lot of time, and companies that are investing right now into quantum computing, they are going to be the ones that will reap the benefits in the years to come, because they will be having what I call the first movers advantage. And that is a big thing in quantum computing, because once you get the first movers advantage, let's say you are a car manufacturer and you use a quantum computer to get to create a material that is so much lighter and far and makes the car faster, so no other car will be able to catch up with that car, and they will have the IP. So that is where, if people organizations start using quantum computers now, they will have the edge over other industries. So as definitely I said, quantum computing will, as will have multi-million qubits by 20. So at that point of time, we will the organizations that have a head start right now, they will be the ones benefiting. If we act now, we can have that edge in the years to come. So that is where they are also a threat to national security, because let's say some other country develops a quantum computer, so they will be able to hack into government systems, into your bank accounts, in your every single website that is not secured by quantum communications can be hacked. So we need to think about post quantum cryptography as well. So this is how a stack of quantum computer looks like. So at the bottom we have hardware design, test and measurement, system integration, and error correction. So between them, we have the platforms that are there like IBM Quantum Lab or Strangeworks, and then a solution is provided, which is we engage with the customers and we provide them the solution. So, what is the type of quantum advantage? What makes us believe that yes, we are getting some advantage? So, in 2020, Google had made a claim that we can actually use a quantum computer to do a calculation that would take 10,000 years on classical computers, and we could do that in just 200 seconds with a quantum computer. So, that is where the advantage lies. That was called the an experiment that Google made, and that was the quantum supremacy experiment. So now, if we'll think, what is the other applications that we can get and see some advantage? So, firstly, we need to have a useful problem and a fast quantum algorithm, and no fast classical algorithm should exist. So, that is the intersection of all these points. And in order to get that, we have two kinds of improvement. One is the polynomial improvement, and the other one is the exponential improvement. So, reducing the number from 2 raised to the power n to n cube is an exponential improvement. That means that we have made the program so much faster that now we are getting an exponential improvement.
Manan, sorry
Yes.
to interrupt. Can you go to slideshow, please?
Actually, it's not working. I tried, so it's
Okay.
freezing over there.
Okay, okay. No issues, no issues.
So coming back, we have exponential power. What is the use of exponential power? So I'll give you an example. Let's say we have 1 penny, right? And every single day we double that penny. So by the end of 31 days, we will be having 21 million dollars. That is the power of exponential growth. If you look at some great investor, Warren Buffett, so he said that compound interest is the most valuable thing that mankind, not mankind, but the most valuable thing to double your money or double your investment. So in the similar way, quantum computers are also doubling as we add every single qubit to them. So that is the power of exponentials, and that is, once it is coupled with first movers advantage, then it's a steep curve, that's like going upwards and upwards, like I'll show you over here. So right now we have 30 qubit quantum computers, 80 qubit quantum computers, and we cannot simulate more than 30 qubits on classical computers. So that is where we have already reached the limit of classical computing. So if we have all the computers on earth, that would mean that we have the same computational power as an 80 qubit quantum computer. And like I earlier said, if we have more than 300 qubits, we'll have all the atoms in the known universe. Even if we combine that, that would be the exponential computational space of that. And on the left hand side, if you'll see, there are some problems that can be solved faster on a classical computers, but simulating a quantum computer on a classical computer is not feasible. So earlier on, we had if you look at simulators work, so for early stage applications we can use a simulator and we can develop a prototype application. But in order to simulate that, we need more qubits. We need so right now IBM has the highest quantum computer. They have 127 qubits. But apart from that, there are companies like Pascal. So they have neutral atoms, and they have already shown that we can have 1000 qubits quantum chips with neutral atoms. So that is where we also need to think which technology is going to be the winner, because right now we are at a stage we don't know which technology is going to give an advantage amongst the iron trap or the superconducting qubits. So we are not sure yet. So we are in a stage where we have a producers and consumers divide. So right now the quantum producers are very large, but the quantum consumers are very less. But in the near term, those producers are going to be very less, and ultimately every big organization is going to end up using a quantum computer. Otherwise, they face a risk of getting staying behind in terms of technological development. So now I'm going to talk about noisy intermediate scale quantum computers. So this is what the IBM System 1 looks like. I hope many of you have seen that. It sits behind the same glass that the Mona Lisa has. So the Mona Lisa is placed in the Louvre in France, and it has the same glass that this quantum computer has, and they are stored at temperatures of millikelvins. So that is where they are so cold that they are colder than outer space, and that is what makes them so unique. And it's a marvelous technology in itself that we have reached. So they have what we call artificial atoms inside them. So I'm going to talk about them more, and as I said about the quantum supremacy experiment earlier, so this is what a quantum hardware stack looks like in terms of a superconducting quantum processor. So we have the control hardware, then we send microwave signals down to those qubits. So we have qubits on the chip. So this is the chip, how it looks like, and we send microwave signals and then we manipulate those signals. And depending on that, we have two factors: one is the coherence and the other one is the fidelity. So coherence is how long can a quantum state exist, and fidelity is how accurate that state is. Suppose we need to get one, so if it's coming to 0.9 or 1.1, so that is what fidelity is. And we need to develop better quantum computers, we need to make sure that these two factors are we work on them the most. So this is what so this is what actually Google claimed. And then after a few months, IBM claimed that we can do the same task in 6 days, as I said about the quantum supremacy experiment. So that is where these companies are clashing. They are saying that what we can do in 10,000 years, we can just do that in 6 days. So right now also, if you'll see, a few months back someone had made a claim that the quantum supremacy experiment can be performed on classical computers. So that is where we see some advantage, but sooner or later we see that classical computers are winning. But that is not going to be the case in the next 5 to 6 years, because then quantum computers will be entering into a different era. So this is what a superconducting QPA looks like. As I said, about the coherence and the fidelity. So on the right hand side, you can see the qubits. So we are sending microwave signals to these qubits and manipulating them depending upon the frequency. So this is what the the stack looks like, the 3D chip. So we have chips that are 3D, and on the top side we have transmons, on the bottom we have the readout layers. So that if anyone is more interested to get to know about all these things, so they can check out the Qiskit metal. So that is one very interesting area if you're into electronics engineering or any other field and that excites you, so you can work on that, build quantum chips. So apart from that, then we have the cryogenic system. So these systems cost about $1 to $2 million, and this is how they are kept. So we have a dilution refrigerator, that is what it is called, and then we have the gas pumping over there, the compressor, and all those stuff. Now I'll talk about fault tolerant quantum computing. So what is fault tolerant quantum computing? Now I've told you about the NISQ devices which are prone to errors and we cannot do anything useful with them. So Google came up with a claim, then IBM resisted that claim, and then we are seeing that there is no application yet of quantum computers in with NISQ devices. Even if we'll get some applications, that will be in the area of quantum chemistry, where we still need 1000 qubits to do something useful. So right now we are just exploring quantum computers, we are just trying to create something that is scalable, so that if we create something for 100 qubits, that can be scaled up to thousands and millions of qubits. So if we'll not do that right now, then some other organization, let's say who is using quantum computers, and they develop those algorithms, then once we will have those 1000 qubit quantum computers, they will be having the edge above every other company. So what do we actually need for for useful quantum computing? So firstly, it should be a manufacturable technology. Secondly, a fault tolerant architecture, and thirdly, it should be a realistic path to scale. So if you'll talk about the IBM quantum computers, there is a certain roadblock with them, where now if you look at what they are trying to do, they are trying to connect quantum computers together, and they are placing chips inside one quantum computer they'll place multiple chips, and with multiple chips they'll connect it to multiple quantum computers. But that is where we cannot do in the teleportation from one quantum computer. We cannot send those qubits from one point to the other quantum computer. So that is where, because we'll be getting some classical infrastructure between them while we are connecting those quantum computers. So that is where the problem of scaling is coming. uh, and we cannot scale those quantum computers to millions of qubits. We can, but we will be having those intermediate classical wires. And then let's say what is the error now in that. So for near term, superconducting qubits can provide promising results in algorithms like QAOA and VQA, but the solution developed using these algorithms are demand and viable to fulfill the requirement. So if you look at this graph over here, then classically simulatable 10 raised to the power 1. Okay. And then for useful error corrected quantum computing, we need millions of qubits, and we are not in that stage. So near term applications, we still don't know. And we are in the 100 qubit 10 raised to the power 2 stage right now. So we don't know where we will be seeing the advantage. It can come at 10 raised to the 5, 10 raised to the power 5 also, or 6 also. So now I'll show you what an ideal experiment on a quantum computer looks like. So this is what we implement a gate, and we think that the ideal experiment is going to give us this result. So this is the circuit depth, how many times we do the we iterate the circuit, and this is the measured z state. So this is what a noisy ideal experiment should look like. But now, if you'll see the real experiment, so due to the noise in the quantum system, we are getting these kind of results. So this is not favorable to give an outcome. Suppose we are looking to get a solution, and then we give it to a quantum computer. So these are the results that we expect. We get so much noise. That is where we need to have some error correction schemes, so that these kind of noises can be mitigated from the quantum computer. We have projection noise, incoherent noise, then coherent noise. So all these things affect the result of the quantum computer, and it affects the outcome of the application. So now how do we try to build from these large quantum computers to a small quantum computer, to something that we can scale? So if you'll see, then right now CMOS technology is one of the most favorable. And due to the fact that these quantum computers use coaxial cables to send microwave signals, then how much wires can be fit? So that is going to be a question, right? So that is going to be adding more and more bulk and weight to quantum computers. That is where now we need to think about additional technologies, something that is not having the same problems that we have with superconducting qubits. So there is another technology, that is the ion trap quantum computing. So let's say we have different. So what we are doing over here is we are trapping an ion first of all in vacuum chambers, and this is how the qubit looks like. If you'll see on the bottom, on the left hand side, we have those dots, and each dot is a qubit, and we are manipulating those qubits. So this is an actual IonQ quantum processor. And on the right hand side, if you'll see, that we can actually connect these quantum computers together via optical fiber cables, and do so that is where it opens the room for interchip teleportation. So that is where now it is possible to do all those stuffs, design quantum computers and then connect them together using the normal wires that we have, these optical fiber cables that we have in our daily for our net connections and all those things. So that is where these machines become so much more powerful. And apart from that, there is another technology that we have, which is called the photonic quantum computers. So for photonic quantum computing, we have all the boxes ticked. So we have something that is called manufacturability, because photonic chips can be manufactured right now and we can scale them. Then we have the control electronics for them that we can integrate on the same chip. And then we also have they don't require us to have millikelvins of temperatures, so they are 1,000 times more capable in terms of cooling. And then for photonic also we can do chip to chip connections with standard optical fibers, so we don't need transducers for in order to do that, and it makes the interchip teleportation possible. So that is what the photonic architecture looks like, and ion trapped. Apart from this, we also have, different other architectures. So we have diamond based quantum computing, where we are manipulating the valencies or inside the diamond. Apart from that, we also have neutral atom, as I said. Then we have another company that is called cold quanta, so that is using some other kind of technology to make quantum computers. So that is where we don't know yet which one is going to be dominating. And Microsoft recently came up with a very very new technology, that is the Majorana firm qubits. So in that case, they have developed something very very useful, and they have shown that it is capable to in fact trap the state into using the Majorana fermions. So that is very interesting development, and we have to think about what can be done in those regards. So we don't know yet which technology is going to be successful, and that is where we need to have an approach that is hardware agnostic, and we need to focus on software applications, so that that is that does not focus on the hardware requirements. So it means that we can have different hardwares, it doesn't matter. We need to focus on the software that can be used on all those different quantum computers, irrelevant of which technology they are made up of. So that is how we can scale things up and do something useful. In order to do that, we will need thousands of qubits, like I said. So this is the value proposition that they provide. So if you are seeing over on my screen, they are accessible, they have room temperature computation, and they are compatible with existing optical infrastructure. Then secondly, they are scalable. So they are network quantum computers, and they have the ability to reach 1 million plus entangled state. Then they are versatile, they have unique set of business applications, and they can also be used in sensing and secure communications. So if you've heard, there's multiple things coming out now. There's quantum internet that is coming, quantum ram that is coming, and apart from that, India also has significant edge in terms of quantum communication, in terms of quantum key distribution. So if you are communicating from your phone, right now they can be intercepted using quantum computers, but QKD prevents that, quantum key distribution prevents that, and we no longer have to think about some middle guy, trying to hear our conversation. So that is the value proposition that they are providing in terms of communication and sensing. So this is how a blueprint of a photonic quantum computer looks like. And let's say we have, so another key number that we need to keep in mind is that the number of physical qubits does not matter. It does not matter how many physical qubits we have. What matter is how many logical qubits do we have. And sometimes this number is 10,000 times the physical qubits. So that means that if we have a 10,000 qubit let's say a 30,000 qubit quantum computer, so then that would mean that we have three logical qubits. So we have to think in those terms, that how we need to scale, how can we scale them to millions of qubits. So the race is open yet, and there is no clear winner. And certainly, in my opinion, there's a lot of scope for photonic quantum computers and superconducting quantum computers as well. But every technology has their own limitations, everything. So it can also be possible that we will be living in a world where they can be superconducting qubits also, and just like we have cars, right? They are diesel cars, petrol cars, then electric vehicles. So each one has their own advantages, so you cannot compare all those things. So it depends on the requirements of the person that is buying the car. And similarly, in terms of quantum computers also, we have different technologies, so they will coexist together. And classical computers, some people also say that classical computers will become obsolete, we won't be using classical computers after we have quantum computers. That is not the case. They will coexist together in terms of a hybrid classical quantum infrastructure. And let's say that your quantum computers are, let's say your cars are like classical computers now. And what a quantum computer is, it's like an aeroplane. So it can take you from point A to point B in a much faster way. And still we use cars, still there are aeroplanes. Just like that, we will be using classical computers also, and we will be using quantum computers also. And they are very expensive right now. If you need to operate a quantum computer, you'll have to pay around 5 lakh rupees an hour to IBM, because that is the case. They are charging $1.6 per second. So if you'll calculate that, that means 5 lakhs for an hour. And that is just the cost to operate them via the cloud. In order to buy them, let's say you are a big organization, they will cost somewhere around 300 to 400 crores. So that is where you cannot afford them yourself, until unless you are a big company, you are working over there. So they will be able to help you out with that. And that is the same case with aeroplanes. You don't buy aeroplanes, right? You just sit on an aeroplane and go from point A to point B. And but you can buy cars. So think of that in those terms, in those aspects. That is the analogy I used to give example to people that want to, that ask me what is special about quantum. So what will happen with quantum computing. So I try to give them a sense in terms of realistic terms, what is going to happen, and how we can compare it with what we are existing to, what we are using today. So in essence of quantum mechanics, I would like to finish my talk. So these are the applications of quantum computing. So we have applications in quantum machine learning, quantum simulation, math, science. It's all on the intersection. So every single industry is going to get affected by quantum computers. Let's say it's aerospace or automotive, logistics, pharma industry, or metaverse, you say blockchain. Every single industry is going to get affected by it. In the same way that computers changed our world, we entered from the age of digitization. Now we are entering the age of quantization. So, and with that, I would like to say, what is quantum? So, quantum is just something that you cannot break down further. So that is the essence of quantum mechanics, and that is how we can harness that properties, and we can create quantum computers. So with that, I would like to thank you all for joining, and I would like to conclude my sessions. If you have any questions, just feel free to ask me any question that you have. Can you guys hear me?
Yes, sir.
Any questions? Anywhere your mind got intrigued, or I was able to anything that comes up in your mind.
So, first of all, thank you so much for this talk. I really am so grateful that I was part of audience. And sir, I got to know about this event because of you only, because I'm following you on the LinkedIn, and
Okay.
I got this link of this hackathon from you only.
Okay.
So yeah, so
That is wonderful.
um, yes, sir. Because in this series of talk, I listen to so many experts, and I'm really getting benefited from their words of wisdom. Sir, my question to you is the last slide. Can you show?
Just once again.
Okay, sir.
Yeah. Yes.
Sir, what I have studied so far, so linear algebra is the language of quantum world. So, in this Venn diagram, uh, what I feel that the math part must
Yeah.
be the intersection in the all the parts of science.
Yes. So science has like broad domains, right? It has biology, chemistry, physics, maths. So this is where in physics also we are using the room temperature superconducting qubits. So that is not correlated with mathematics. So in terms of that maths, yes, we have linear algebra, and in terms of that is very important for doing quantum computers. Is that what your question was?
My question is, means I'm a bit getting difficulty to take this picture because in my mind, what I thought that um, quantum world, means if we are talking about whether it's quantum mechanics or quantum computing, I haven't studied anything from the quantum chemistry or biology, but yes, physics part and computing part I am studying. So my question is that what I studied that a qubit is the linear combination of classical bits, and we use quantum gates, that is the actually unitary matrices. We use the evolution operator, which is the again matrix. We use Hamiltonian, that is Hermitian matrix. So my question is, isn't it a quantum world and math is overlapping to each other, and it's bit you made a bit different circle to the math, and which is not wholly um, um, intersecting with all the spaces with science. I think math part should be a greater one in which every the parts of other fields of sciences are belonging. That's in my mind actually. Maybe I'm wrong, and I'm my perception is a bit different because I'm a scholar of mathematics. So I see everything from the eyes of mathematics. So I'm thinking that mathematics lies everywhere. So,
That is true. That is true. So I'll tell you what. So this is the this picture, right? It's for the applications of quantum computing. Okay. So which means that in science we can apply quantum computing to biology. In biology we can apply it to personalized medicines, bioinformatics, and then all those things. In maths we can apply it to linear algebra, where we can find out. So linear algebra obviously has, let's say, now we have in an equation we have three unknowns, right? So now let's say we have thousands of unknowns. So how much time will it take to solve us those problems, because we have so much of variables, and we cannot do that with classical computers because that would take a lot of time. And in linear algebra also there should be another point over here in maths, that is factoring. So Shor's algorithm helps us factor number faster. So that is an application in mathematics that quantum computers can help us do. We can solve differential equations faster, we can do encryption faster. So all those things, that is the application in quantum computing. And it is also the algorithms that are coming over here. If you see, that is where the, like you said, the gates and the matrices, all those stuff, so they come inside this circle, and it should be big as you said, but yeah, it is what it is.
okay, so these are the application where quantum computing is going to make our life easier and our problems more solvable. Okay, I got it, sir.
Yes, yes, yes.
Thank you so very much, sir.
No problem. Thank you. Any other questions?
Hello, Mr. Manan. This is Priyanka from CDAC Daddy. A very nice talk, and I really enjoyed it because I'm not the person who is working in this direction. But out of curiosity, I just started listening you guys, ki how you guys are doing so much good in this the field. So this was my first or second presentation, which I heard about the quantum thing. So while I'm here in Delhi with the neurocognitive AI and XR related work which I'm doing over here. So just how to make the overlapping between the neuro aspects and the quantum aspects. I started looking into the things. Thanks for nice presentation. And my not a scientific question. My question is something different. What I found and understood by your talk that the your concentration and your focus is toward achieving the more and more speed. What I got. So the complexity of the problem which you can solve in a fraction of seconds. Uh, Second thing, while working with AI and data science related thing, I found that okay, we have availability of data, humongous amount of data, and humongous amount of speed as well using quantum. So, well, sorry, this is not a scientific question, but where are we leading? Means how much speed we are expecting, where we would be reaching, where we would be going with this data and with this speed. So, what is the end point where we would be reaching with this availability of these resources? So, sorry if it is not a very appropriate question, but this is what I got in my mind.
No, no, it's a very appropriate question. It's a good question actually that you ask, that where does the quantum advantage lie? That is your question, right?
Not exactly in terms of quantum. That's okay. By utilizing this, the with the availability of speed by means of bullock cart, then cycle, then rickshaw, then motorcycle, then car, and then aeroplane, as you said. Uh,
Yes.
so हमें जाना कहाँ है?
Yeah, so I'll give you an example. Let's say right now, how many cows are dying due to some disease that is happening, right? So that disease does lumpy skin disease. So that disease does not have any cure, right? So people can use classical computers also to solve those kind of problems, but if we have a powerful quantum computer, right, then we can actually simulate that molecule. We can extract more information out of that molecule using a quantum computer, and then find a cure of that disease. So हमें जाना कहीं नहीं है. We can just use quantum computers and give something useful to humanity, solve problems that were never solvable before. So that is the kind of problems that we can solve using these machines, and they have the power to simulate those molecules in such a way that we can see the quantum mechanical properties. So right now all of us are accustomed to seeing the world from a classical lens, and let's say we change that lens to a quantum lens, so then you will be able to see the world in a quantum way. So, for example, if I give you a red color lens to wear, then you will see the whole world is red. If I give you a blue color lens, you will see the whole world is blue. In a similar way, we need to see the world from a quantum lens because the world is quantum mechanical. It's not classical. And using quantum computers, we can see that molecule and we can see those properties that we had never seen before. In quantum machine learning also, we can extract that quantum data out of that, and we can do exponentially faster quantum machine learning. So the training becomes faster, everything's become faster. So that is where we'll progress, as the technology has been the field in the industry that has advanced the most in the last 30 years, right? And with the advent of quantum computing, it's going to advance even further. So that is where we will be heading into an era where we can do things that no longer we could do. Let's say Elon Musk wants to go to Mars, so he can use quantum computers to accelerate the whole process. So that is where we can the possibilities are endless. It's up to our imagination, our curiosity, what we think we can make use of these quantum computers. I hope that gives you a little bit of insight of what we can do with
Yeah,
them.
you nicely explained that aspect as well. Though that aspect is not a scientific aspect, because my concern was a little bit something different. Like the same question is being asked in case of AI also, with the availability of this data and resources. Where means, well, my question was means it was having a different perspective that is not technical. So that's great. It's nice talking to you. Thank you very much.
Same here, same here.
Thank you.
Anyone else? Anyone else has any
Participants,
questions? Yeah, go ahead.
participants can feel free to ask questions when I'm here.
All right, I think we don't have any more questions.
Yes, I
So,
think we arrived at the end of our session.
so perfect, perfect. Thank you so much, everyone who has joined today. It was wonderful presenting to you all and answering all your questions. So, if I am given the opportunity again, I'll be happily coming over here and interacting with you, everyone. So, just feel free to reach out, Dharni, and we can definitely collaborate further.
Sure, sir. Thank you for your wonderful and detailed presentation, and it was extremely informative about the fault tolerance of quantum computing and the applications of quantum computing. It was very informative.
Thank you so much. Thank you so much.
Thank you, all participants, for joining and supporting our event. And I would like to thank Dr. Manjula Gandhi for constantly supporting and leading us throughout this session.
Thank you, Manjula ma'am. Take care for now. Bye bye.